Hello everyone, welcome to part 4 of the Hidden Markov model video series. So in this video we are going to talk about the third problem of HMM, which is the training the HMM, and we are going to use the famous Baum-Welch algorithm to do this. If you have come to this video directly, I would highly recommend you to go through part 1 and part 2 of the video series because those are extremely important to understand what we are going to cover in this video, and I'm going to give the links of those videos in the description of the video. So let's dive in. The first thing is, let's see what a typical sequence looks like. Right? Typical sequence in a data set for HMM looks like. So in the data set, normally you have sequences, and this is just one sequence. And for that sequence, you simply have the sequence of observations. So here, we are observing tumor level or ctDNA level of the patient in different time steps. So we have high tumor level, moderate tumor level, and then in the last 3 time steps, we have low tumor level. So these are our observations from O1 to O6 in the 6 time steps. Now we also have hidden states, but we don't know what those states are. This is what our typical dataset looks like in HMM. So what we also know is, we also know which hidden states are actually possible. So we know that we have early stage, mid stage, and late stage cancer patient. So S1 to S6 can be early or mid or late, but we don't know what they are. We also know that our observations are actually 3 possible observations, which are low, moderate, and high tumor level. We also have a transition matrix for transitioning from one stage or one state to another. We also have observation matrix or remission matrix where we say that what is the probability of observing something given a certain hidden state. We also have the initial probabilities, which is called pi of the hidden states. Now the thing is, these parameters, these probabilities, A, B, and pi, they are not known. They are not known in advance, and these are something we have to train the model for. So we have to infer these parameters. So in this tutorial, we are going to actually see how we can infer A, B, and pi from sequences like these that are given in the training dataset. So first of all, we need to recap a few things. We need to see what alpha ti is. So alpha ti is an assisting variable which we need to calculate, and it means what is the probability of staying at state Si at time step t while you see the observations from O1 to OT, right? In the time step T1 up until time step T, right? Given the model itself. So what is the probability of that? You also need to get the probability, the opposite thing. So here you see that we are fixing a state Si at time step t, and we are assuming that we are actually assuming all the previous, like the past, well, what happened in the past, what we observed in the past. So in beta ti, we observe everything in the future. So ot plus 1 up until ot, given we are at state Si at qt. Now, how exactly are we going to calculate alpha ti and beta ti for all the time steps and for all the states? That is described in detail in part 2 of the video series where we describe forward-backward algorithm. So most definitely go through it first if you have directly jumped here and don't know about the algorithm. So you know that in order to estimate alpha and beta, we require pi a and b, but this is what we want to estimate. So how can we actually derive alpha and beta? Very simple, we randomly initialize pi a and b. Initially, we just make sure that those things add up to 1 because these are probability distributions. So the next thing we have to do is we have to calculate this parameter called psi t between I and j, state Si and state Sj. Psi t means we are calculating this at time step t. That means we are calculating the probability of Si, state Si being at qt, and state Sj being at time step t plus 1, given our observations. So this is how it looks like. You can have any state previously, you can have any state afterwards, but at time step t, you should have Si, and at time step t plus 1, you should have Sj. That is what we are desiring in this particular variable. So just to show visually how you get this formula, you have alpha ti, which actually takes care of all the past things. You have beta t plus 1j, which takes care of all the future things. And in the middle, you have the transition probability aij. And also, you make some observations on time step t plus 1. So assume that the observation is ot plus 1, so you have the probability of observation. So if you multiply all these 4 things together, you are going to get psi t. But since psi t is a probability, you need to normalize it. So how do we normalize it? We simply divide by the sum of all possible combinations of all the states I and j. Right? Very simple. So the next variable that we need to calculate is gamma t. So what is gamma ti? Gamma ti means at time step t, we want the state Si to be there. And what is the probability of that? So it is very simple. So if you know probability, you know the theory of marginalization. So if we want to calculate the probability of Qt equal to Si, we can simply sum over all the states that Si can transition to. That is why we sum over psi t of ij from j equal to 1 to n. So all the states Sj to which we can go from I. If we actually sum those things up, we are going to get lambda ti. And this picture also denotes that because we are not considering a fixed Sj right now in this figure. Sj can be anything from S1 to Sn. And we are just adding up all the psi t of those different S's, and we are getting the lambda ti. So, okay, we now know how to get psi ti, ij, lambda ti, alpha ti, beta ti. We know those things. So how are these things going to help us? So first of all, we are going to assume a simple scenario where we have only one sequence of observations as part of training data. Understand that in the training data, we can have many sequences of observations. Maybe sequence 1 has 10 observations, sequence 2 has 5 observations, sequence 3 has 20 observations, I don't know. But just to keep things simple for now, we assume that there is only one sequence of observations. So if you think closely, if we sum from t equal to 1 to t minus 1, that means all the time steps of lambda ti, we're actually going to get the expected number of transitions from Si. What was lambda ti? If you remember correctly, lambda ti was probability of staying at Si at time step qt. So if we sum up all the t's, we are going to get the expected number of transitions from Si, or expected number of times we stay at Si, basically. The same thing. Similarly, if we sum up these ij across all the time steps, we get the expected number of transitions from Si to Sj. It's very simple, very similar. Now, these two parameters are going to help us a lot in order to get our pi a and b. So I will show you how right now. So for pi, let me show an example. Pi I means the initial probability of state I. So probability of getting hidden state Si at time t1, because it is initial state. Initial means t1. And at t1, probability of staying at state Si is simply lambda 1 Very simple. What is the probability of transitioning from state Si to state Sj? Very simple. The number of transitions you make from state Si to Sj and total number of transitions you make from Si. So total number of transitions you make from Si is summation of the lambda ti's, and the upper one is the summation of the psi t ij. So this is how you can get the transition matrix for all the combinations of Si and Sj. And finally, you have the observation matrix, remission matrix. So if you want to get the probability of observation Vk given a state Sj, then this is what it looks like. So in the numerator, you have the number of times when you were at state Sj while observing Vk. So you have to observe Vk as well. Only staying at state Sj is not enough. And in the denominator, you just say how many times we actually stay at state Sj. No matter what we observe, we don't care what we observe right here. So very simple. You just add up all the lambda t's. But the difference is in the numerator, you just put this condition. So you add lambda t's only for those time steps where the observation is Vk. That is the only thing. So this is how simple it is to calculate these three parameters from these existing variables. Now, you may say that, okay, is our algorithm over? Because we have successfully obtained pi a and b. But the thing is, no, it's not over yet. A few more steps. So this is an iterative process. The Baum-Welch algorithm is an iterative process. You randomly initialize a, b, and pi. So in the E step or expectation step, you calculate alpha, beta, gamma, and psi for your sequence of observations. And you use these things in the maximization step M to get A, B, and pi. So A, B, and pi is trying to face some sort of update. So after updating A, B, and pi, you again calculate to the E step, calculate these four things. Then after calculating these four things, you again get to the M step and recalculate A, B, and pi. So A, B, and pi is now getting updated and updated and updated. Now, how many times you actually do this circular iteration? So you keep evaluating observations after each new HMM model. Whenever you get a new A, B, and pi, you have to evaluate your observed sequences. You have to evaluate their probability. And how exactly we evaluate a sequence of observations has been described in part 2 of the video series in the forward-backward algorithm, where we actually describe how we solve the evaluation problem of HMM. So make sure to check out that video. So when we see that the evaluation probability does not really increase much, we can terminate. That means our model is not getting any better now. So we can terminate the model. One thing very important is this algorithm is not guaranteed to reach the global maxima. That means, you cannot guarantee that the ABN pi are the best ABN pi possible, but it will reach a local maxima. That means it is a good enough ABN pi, nevertheless. Okay, now we talked about only one sequence so far. What happens when you have m number of sequences of observations? Now this m should have been capital, pardon my mistake here. So suppose this is your first sequence of observations, O1, O2, O3 up to OT. So one is for the first sequence of observations. Then you have this O2, where you also have a sequence of observations, and finally you have OM, the mth sequence of observation. You see that the T is different for different sequences because these sequence lengths don't need to be the same. They can be different for different sequences, and that isn't any problem for HMM. Now, the E step for calculating these four parameters remain the same. There is no difference. The only thing is you need to calculate alpha, beta, gamma, and psi for each individual sequence separately. So O1 will have one set of alpha, beta, gamma, psi. O2 will have another set of these, and so on and so forth. So basically, for m sequences, you are going to have m set of these variables instead of a single set. Okay. Now that you know how to get the E step, let's talk about the M step or the maximization step. So in the M step, you now have to do summing over the sequences. That is the only difference. So let me explain how. So you see this formula. So in the transition probabilities, I have marked the changes. So instead of just putting this part, you also have to sum over all the sequences now, which is pretty natural, both in the numerator and the denominator, for both the transition probability and the emission probabilities. And also there is this thing Tm, because as I said before, different sequences have different sequence lengths. So the summation has to be according to the length of that particular sequence when you are summing those probabilities up. And finally, in the initial state distribution, you again do the summing, but now you have to also divide by the m, and that is the number of sequences. That is the difference, a very minor difference, and I think it's very understandable. So now you understand exactly how Baum-Welch algorithm is worked out for HMM training. A few concerns. You now have all the probabilities using the Baum-Welch algorithm, but how do you know which SI indicates which state? Let me clarify this further. So suppose you have three hidden states, as we mentioned before: early, late, and mid-stage cancer. Now the only thing HMM training knows is that there are three states. It doesn't have any idea about the semantics of those states. It doesn't know what early means, what mid means. It doesn't know about those things. So HMM, after the entire process of Baum-Welch, may assign early stage to S1, mid stage to S2, and late stage to S3, or it may also assign something else. For example, mid stage to S1, late stage to S2, and early stage to S3. Or you can think of other combinations as well. So how do we know? Like what is S1, what is S2, and what is S3? Because we need to know those. Because when a new sequence of observation appears, we need to be able to actually say what are the possible hidden states for those observations, because that is the primary goal of HMM. So the way we can do this is, after HMM training, you are obviously going to get observation and transition probabilities, because that was the goal. You will get the A and B. So suppose, for this example, the example that I'm talking about, suppose we know that early stage cancer tends to have low tumor level or low ctDNA level. These are prior knowledge. So if we see some state with high probability of low ctDNA observation, we can assign that as early stage. Fine, done. Let's give another example. Suppose you know that early stage cancer is less likely to transition directly to later stage. Now, if you see that some state has a very low transition probability, if you see that your earliest stage, the earliest stage identified right here, has a very low transition probability to some other S, then that's probably your late stage. So basically, you can actually learn about which S represents which state through some prior knowledge, through some domain knowledge, and it shouldn't be a big deal. So far we have seen the case where we only have the observations in our data set and not the hidden states. But what if we are also provided with the hidden states in our training data? You can have a very high quality training data where you have the hidden states and the observations. That is actually good for you, right? Because that is high quality data. So your data may look like this. This may look like one of your sequences. So these are your observations: high, moderate, low, ctDNA burden. And you also know the cancer stages, which are the hidden states, right? So now what are you going to do? First of all, in such cases, don't use the Baum-Welch algorithm. Don't use that. You can actually get your pi a and b through simple counting. So what do I mean by this? Let me clarify. For example, in order to get pi I, the initial probability of state Si, you simply count the number of times state Si appears in your entire data set. And you count how many times, I mean at time step T1 obviously because it's the initial probability. And you also do the same thing for other states and you divide the summation, divide by the summation. So if you have three states, late, early, and mid, and maybe your late stage comes at T1 maybe 20 times, and the other ones come 5 times each, pi for late stage will be 20 divided by 30. That's how simple it is. Same thing goes for the transition function. For example, the number of transitions from Si to Sj, you can count that. And you also can count the total number of transitions from state Si in the data set. Same thing goes for here. You can count the number of times in state Sj while observing Vk. And you can also count the number of times we were in state Sj. You can make those counts. And if you can make those counts, then that's it. You just put in those numbers, put in those counts, and calculate the probability. You don't need any Baum-Welch algorithm here. But suppose there's this third case where you have only a few of the hidden states, you know a few hidden states, but many of them are not known. So it looks something like this. So some of the states, hidden states, you don't know, and some of them you do know. Then what are you going to do? Actually, it's not complicated. In these cases, you can actually form this kind of graph. So normally your graph will look like this. So everything is connected to everything. But you now know exactly what state is there in particular time steps. For example, in time T2, you only have late stage, so the arrows will go to late stage. And again, in T4, you know that the arrow should only go to early stage. So you just put one node right here. And so using this graph, you can actually calculate the alpha, the beta, and also the psi, the lambda, those kind of things. So that's the only difference. Now, a very, very important question. In many times, when we use HMM in bioinformatics or computational biology, obviously doctors, clinicians, they are the experts, they have the prior knowledge. So how do we actually incorporate that prior knowledge in HMM training? So let's see. So suppose we want to impose the following prior knowledge in our HMM training. I mean, we already mentioned the problem where we have the different cancer stages and different tumor levels, right? So the first knowledge is the patient is more likely to start out from late stage. So when he has been admitted to the hospital, he's probably starting out with late stage cancer. The second thing is early stage patients are less likely to transition directly to late stage. So it will, I mean, he can transition to late stage at one time, but not immediately. So the final thing is early stage patients may be more likely to have low serotonin level. Now these are just assumptions. I mean, I'm not a doctor, by the way. So, but doctors can actually give you this kind of prescription. I mean, which you can impose on your model to better your training process, to better your estimation process of the different probabilities. So first of all, the change in initialization. So obviously, late stage cancer is more likely to begin with. So pi late should be much higher than pi early and pi mid during initialization. And also, for the second condition, probability of observing late, probability of transitioning to a later stage from early stage should be much lower than early to mid and early to early in your initialization. And finally, probability of seeing a low tumor level at early stage should be much higher than the other two cases. So during initialization, instead of initializing everything randomly, you can actually initialize them in this way so that you already bias the model towards some assumptions. The E step, there is no change. You just calculate your alpha, beta, gamma, and psi as we did before. So M step is more interesting. So in M step, for pi calculation, you use some pseudo counts. So you provide the late with a high pseudo count of 30 and early and mid with a lower pseudo count, and you add those pseudo counts up. So you can see that if we are working with late stage, then we are going to add 30 in the numerator, and in the denominator, we are only going to add 40, which will bias the whole probability a lot towards the late stage. And the opposite is true for early and mid. Now, there is a term called strength in these pseudo counts, and also this is called Dirichlet prior. So you can read about Dirichlet prior in detail, but that is not the purpose of the video. So what is the strength? So here the strength is 40. That means your observations or your data can actually alter your assumptions. Like your data can be so strong that it can alter the assumption that late stage should be more likely. right? Maybe your data, there is a whole lot of patients with earlier stage, starting from earlier stage, right? There can be those patients. So if you really want to make the assumption stronger, you have to assign larger numbers here. So you can assign 500, 500, 3000. I don't know. You can do that. Okay. Now, the next thing that we need to also know is how to get transition. So we talked about early stage bias. So we want the early to late to be less probable. So we give 1 here and we can give 2020 here. And again, if we want to make this strength higher, we can assign maybe 200, 210 right here. And so in this calculation of probability of going to some state SI, given that we are in early stage, we can add these things right here, 0 comes. And same thing we can do for the observation. So we know that the observation of low serotonin level when we are in early is higher compared to the last one. So we can add a high number right here. And we can add these things up in the numerator and denominator. So this is how we can bias our model towards our assumption. And that is a very good idea. So that's all about HMM training. So I hope in the next video, I'm going to talk about some continuous case of observations and also how you can actually work with a feature vector of observations. So I'm going to talk about that, and I will put the link of the video in the description. So if you enjoyed the video, feel free to subscribe and share the video. And also you can donate to our channel via the link given in the description. That helps us incredibly to make more videos like this. Thank you very much.